Hello, welcome to CUG. My name is Mrinmoy Bhattacharjee. I'm from the Cloud Mobility Manager R&D team, and I'll show you an AI/ML model that we are developing for forecasting trajectory or location of UVs. Now, why do we want to use an AI/ML model to forecast location of UVs? First of all, let's back up a little bit. This particular model runs on the access mobility function in the core network. And the access mobility function is really efficient in finding about 80%, 70 to 80% of the UVs which have lost their or where the RRC connections are down. So that is the good news. But 20 to 30% of the UVs, what we have seen is we kind of lose the location information because of various reasons. Maybe the UV forgot to give us the location information. Sometimes, the location information is given to the AMF very infrequently. And to find those UVs, the AMF has to spend a lot of AMF to radio network bandwidth. And in some cases, it amounts up to 30% of the bandwidth that the AMF uses to talk with the radio network. And this is where AI/ML-based location forecasting model actually comes in. And why AI/ML? Because AI/ML has the ability to classify behavior of large population of UVs as they move from G node B to G node B. And our entire area is a geographical area which has thousands of G node Bs, and you have millions of UVs that are going from one G node B to another G node B, then to the next one, then to the next one over course of time. And that's where our problem is. We have to find these UVs in that particular network. And that's where AI/ML comes in, because it can actually effectively use various techniques to find the location of these UVs. Now, why do we want to do that? That is because about 30% of the bandwidth that the AMF generates towards the radio network is sometimes wasted because we lose the location of the UV. And if we can reclaim that bandwidth by efficiently pinpointing the location of the UV, we can actually free up that bandwidth that is wasted, as a result of which the behavior or the performance of the radio network improves. Secondly, it also improves the end user experience, because now you have UVs that we can reach much faster because we know the location of the UV through the forecasting of the AI. Secondly, we have been able to free up bandwidth in the radio network, so it works very, very efficiently. So let me go to the next slide. Let me just describe a little bit about what you're going to see in this demo. First thing that we are claiming is that we want to improve network efficiency. So we are going to showcase the AI/ML models that we are building to efficiently forecast location of UVs. And by doing that, what happens is it reduces the amount of traffic that the AMF generates towards the G node Bs and the radio network. And it also reduces the chances of inducing congestion in the radio network. Secondly, what we can do is intelligent resource optimization, because the bandwidth that we will end up freeing up, it can be given back to the operators, and the operational cost of those sites can be reduced. Thirdly, user experience. We can improve user experience by speedily reaching the UVs, and the round-trip delay that we incur in a big network like the one that the AMF supports is related to how congested that network is. More packets in the network, more time it takes for us to reach a UV and get a response back. And if we free up those bandwidths, we can actually reach those UVs faster. So that ends up improving the user experience, end user experience. So let me talk a little bit about the dynamics of UV trajectory modeling. So what we do is we use our learning for UV movement from various customer sites. So this is really this model is built with knowledge of movement of UVs from different customer sites. So we bring that information in and we build traffic models in-house that mimics what happens in those customer sites. And that basically has representation of UVs going to different areas of the radio network. So that is the exploratory data analysis phase. After that, we settle on a set of models, and then we move on to training those models, which is in the middle column. So what we do is we give the traffic data to the model, and we train the model, because basically we show different patterns to this particular model. And once the model gets trained, which means that the model has very high efficiency of locating UVs, and we kind of settle on 95% or more efficiency or accuracy, then we say, okay, we have a trained model. How do we use this model for serving our purpose? That means we have to give this model UVs that the model hasn't seen before and let the model forecast accurately where their location will be. So that's basically the dynamics of the AI/ML model building. So with that, let me take you to our lab to show some examples. All right, let me take you to our lab where we are building this model for UV trajectory or location forecasting. So the first thing that I want to bring your attention to is this CSV file. It's a simple looking CSV file, but this file has the location and trajectory information of thousands of UVs, which are randomly picked up from different geolocations. And why different geolocations? Because depending on the geolocation, the behavior of population in those locations and their movement patterns could be quite different. So it's very, very important for us to basically randomly pick up the geolocations and make sure that we have maximum coverage. And maximum coverage, what I mean is that UVs moving through different G-node Bs so that we can actually come up with a pattern for each of these locations. So once we have done that, we pre-process the data. We have the UV ID, which is the subscriber ID. We have a timestamp. What was the last seen or what was the last location of the UV in terms of G-node B? What was the last seen tracking area? And then the previous G-node B. Now, if you were to look at the software, you're going to have just that information. And that's the reason we collect this data over the course of multiple days, 3-4 days. And what that does is that it gives us the actual movement pattern over the course of a day, multiple days, as UVs move to different parts of the radio network. So once we have all of that, we pre-process the data. And let me show you something. This is the first view of all the UVs that we have traced. On the y-axis, we have G-node B ID. And on the x-axis, we have timestamp. Now, if you look at this, and each of these colors are different UVs that we are trying to model, we're collecting data with. Now, if you look at this data, it doesn't tell you anything. We cannot model anything. This is all over the place. So that's where AI comes in. So we use different clustering mechanisms, different distance matrix to say, go ahead and cluster these UVs into different geolocations. And what comes out is this. So in this particular experiment, we ended up with 10 clusters. What you can see here is that there is a pattern which is actually coming out. So this is our cluster number 1. These are the G-node B IDs. So it goes from 0 to 3000. And this is timestamp. And you can see much less number of UVs are there. Each of the different colors are movement patterns of different users, which are, these guys. But still, you can see there is a pattern, but it's not a very clear-cut pattern. So we have more work to do. Here is cluster number 2. It's a little bit more busy. Here is cluster number 3, a little bit more busy. So what we do is we deploy another set of distance matrix and time series calculations models, and we subcluster each of these clusters into smaller subclusters. Now, a very clear-cut picture actually comes up. This is cluster number 1. And a parallel to this cluster is that you have tour groups. Each of these peaks are different tour groups. Think of it as different tour groups. So, you're going from Helsinki to Espoo, looked at Nokia, came back to Helsinki, and then you picked up another group. You went to Nokia, saw the place, came back. So this is one type of cluster that we get. Second type of cluster that we get is UEs with very well-defined behavior. So they're going to work, maybe going to lunch here, getting out of work for a cup of coffee, and then straight back home. And over the weekend, straight back home may break down because people may actually go to a bar. So these are the different types of clusters that we get. And then there is another type of cluster that we get, which is kind of random. And these are UEs, these are delivery people, for example, Uber Eats, somebody who is delivering mail. Those are the hardest ones to actually model. So once we have come up with these clusters, let's focus on this well-defined one. So what we want to do is for this particular cluster, you see the wide range of G-Node Bs. If we didn't have this model, when we have to find a UE for which location information is not that well defined, you have to go from 500 to 3,000. That's for one UE. That many G-Node Bs get notified. Find me that UE because we couldn't find it from the last location. And think about it, if 10 UEs do that, for 10 UEs, we have to do that 10 times 3,000. That's a lot of messages we are putting in the radio network. So what we say is that come up with an average trajectory for each of the clusters. In this case, we ended up with 30 clusters. In reality, in deployments we measure, we will end up with 80 to 100 clusters. That will be manageable. So here is the average trajectory. Basically what we say here is that for this particular cluster, this is the most likely direction the UEs inside this cluster will follow over the course of time, and these are the G-Node BIDs. Now, once we do that, then you might ask me, so you got this beautiful average trajectory, what good does it do to me? So this is where my UE comes in, my device, and this device is not very good because it doesn't send location updates most of the time. So we say, okay, can you tell me, we ask the model, can you tell me what's going to be the next possible location of this particular UE? So then our model takes the location, some past information of location information for my UE and goes through all of these clusters and then say, which one of it this guy matches best? And we use a lot of criteria. We use regression techniques, time series techniques to do a match. And here is the result. So the red line is the actual movement of my device over the course of day. We didn't give this information to the model. What we gave is some past information. If you can see my cursor, we gave some past information. And the model accurately forecasted. You look at the green line, and it said this is supposed to be the location of the UE over the course of the day or over the course of some time. And you look at the forecasted value and the actual value. Forecast is green, actual is red. They're very close together. So if we step back now, if we have to find this UE, we don't have to go page or send messages to 3,000 G-Node Bs. We can send it to the most probable location plus minus a few. And that buys us back a lot of bandwidth. That we can actually give back to the radio network. So that's the whole beauty of this particular model. So here are the key takeaways of this particular AI/ML model that we are building. First takeaway is the AI/ML models, all the use cases, this is not the only use case, we have 10, 15 other use cases. They are all integrated in a machine learning service inside the CMM, the Cloud Mobility Manager, be it MME or AMF. Second thing is that this particular AI/ML model is able to accurately forecast a location of a UE moving through the radio network. And this solution is available as a POC in 25.3, and we'd like to deliver it as a solution fully tested and maybe hopefully with the help of some friendly users in 25.7. What does it buy us? Efficient UE paging. It improves the success rate of UE paging through UE location with high accuracy. POC 25.3, delivery 25.7. And what does it buy us again? Reduce the bandwidth that is wasted or devoted to finding UEs with no RRC connection. Same delivery timeframe. In the future, what we want to do is we would also like to create categories of these UEs. I mean, some UEs are easy to reach, Some of them are a little harder. Some of them are even a little harder. Some of them are very hard. And what's the use of coming up with these categories? We would like to help our customers to do network planning with this particular information. And finally, we would also like to generate heat maps towards the end of 2025, where we will basically be able to tell that what different areas of the radio network are busy at what time of the month, what time of the day, what time of the year, so that it helps you do network planning. And finally, we would like to use this model to also prevent congestion in radio network. And then if there are any anomalies taking place, we can use these models to detect those anomalies. So thank you very much for listening to me.